Bismillah ar-Rahman ar-Rahim. So last time we talked about analog signals. We characterized the analog signals by a set of parameters, including the amplitude and phase and frequency, and we discussed how to measure these parameters for a periodic analog signal. We also talked about the composite analog signals, which are the signals that can be represented using more than one simple analog signal like sine wave. And we have discussed the Fourier theorem, which states that you can represent any kind of analog signal, whether it's periodic or non-periodic, using multiple simple analog signal like a sine wave with different amplitude, phase, and frequency. If the composite analog signal is periodic, you have finite number of sine waves in the frequency domain. If the composite signal is aperiodic or non-periodic, then you have infinite number of sine waves to represent that signal, which results into a continuous frequency domain representation of that signal. So if you take this analog signal and transmit the analog signal on the transmission line, this is what we refer to as analog communication. So for analog communication, you take analog signals, you transfer analog signals over different transmission media without any manipulation. And in that case, we call it analog communication. And that was the case a few, decades ago. So later on, we started to talk about digital signals. And digital signals are a way for us to represent the data into ones and zeros. And the motivation for this was the fact that if we convert the data into ones and zeros, we can manipulate and we can process this data more efficiently. However, that created a new paradigm of what we call digital communication, where we want to convert these ones and zeros into digital signal. And by digital signal, we mean the signal that has a fixed duration in a duration of time. A fixed amplitude in a duration of time. Okay? And it has طبعا in general finite number of predefined number of signal levels in the time domain, right? So we call this a digital signal. So if we represent the ones and zeros into a digital signal that looks like this, the challenge now is that when we transfer this digital signal over any transmission line, these kind of sharp changes, okay, in the signal level creates a bit of a challenge, which we will talk about today. We also notice here is that in general, these digital signal are in general or very commonly non-periodic. Okay, so these digital signals are non-periodic very frequently. So for digital signals, we rarely talk about periodic digital signal. Therefore, we don't actually have the notion of a cycle. So the concept of a cycle for the digital signal is not valid anymore, because very commonly we talk about non-periodic digital signal. Therefore, we need to have a specific parameters for the digital signal, which we need to talk about today. So these digital signals are characterized by different parameters compared to the analog signals, and in particular the periodic analog signals. So we need to talk about the concept of a bit rate, okay, as opposed to the cycle duration for the periodic analog signal. We need to talk about the bit length, which corresponds to the wavelength of the periodic analog signals, okay? And we need to talk about the representation of the digital signal, okay, as a concept, as a composite analog signal. Wow, okay, so we talked about the fact that any signal can be represented using simple sine waves, including digital signals as well. However, we will see بقى, for the case of digital signal, what is the challenge, okay? So we talked about this, we talked about the digital signal in a way in network 1 when we discussed the non-return to zero, okay, and multi-level representation. So we talked about non-return to zero, the fact that we represent the 1 and zeros with a simple digital signal that has fixed voltage level for the 1 and fixed voltage level for the 0. Okay, so this digital signal represents this combination of ones and zeros, and as we can see, in general, it is not periodic, it's non-periodic. It does not have a fixed repetition that repeats over time, right? We also notice here the fact that if we have these number of bits and we want to send 8 bits per second, which means that we have 8 of these bits in a duration of 1 second, right? If we change this digital signal representation and increase the number of levels, okay, instead of having 2 voltage levels only, we can have 4 voltage levels, as you can see here. If we have 4 voltage levels, we can represent 4 different combinations. And as we know, the fact that if we have the number of levels L, it's actually it gives us the fact that we have the number of 2 to the power n, okay, whereas n is the number of bits that we can represent. In other words, if we have if we have L equals to 4, n equals to log 2 of L, okay? So if L equals to 4, this gives us 2 bits, right? So if we have 4 combinations or 4 voltage levels, this will allow us to represent 2 bits for each voltage level, okay? So this will in fact be good news, because then we can represent 16 bits in 1 second in the exact same duration of this signal here, okay? So in other words, we can increase the number of bits per second, or what we call the bit rate, by having multiple signal levels, okay? So the bottom signal has a higher bit rate compared to the upper signal here, because of the fact that we are using multiple signal levels. So this is what we refer to as the bit rate, and the bit rate is affected by 2 things: the bit duration, okay, this bit duration in that case is 1/6 seconds, and the number of levels that we are allowed to use in 1 bit duration, okay? So these 2 factors allow us to estimate the actual bit rate of this digital signal. This part, okay? So the duration where the voltage is allowed to be fixed in the digital signal, right? And the number of levels that. So in other words, if a digital signal has 8 levels, this digital signal can represent three different bits. Okay, so if we have the ability to have 8 different voltage levels, we can actually represent 3 bits, which means that if we have n bits, if we have the duration of one voltage level as مثلا 6, like the example in the previous slide, then by having this, we have 3 times 6 different bits per second. Okay, because in each duration of time, we have 3 bits represented. So in that case, we have 18 bits per second. Okay, if we were to use 8 voltage levels to use in each bit duration. Type. So this example here allows us to calculate the bit rate. Before we get to that, there are 2 definitions now. There is the bit rate, and as we said, the bit rate is the number of bits sent in 1 second. The number of bits sent in 1 second, and that depends on 2 things, as we said. It depends on the voltage duration, okay, and the number of voltage levels. Okay, so the voltage duration here we refer to. So these 2 things, okay, allow us to calculate the bit rate. Another important definition, which is the bit length, which corresponds to the wavelength. As we said before, the wavelength is the distance that the signal propagates, okay, in a duration of time equals to the cycle, or capital T. And this is valid for periodic analog signal, right? For digital signals, as we said, digital signals are non-periodic in nature. So we do not have the concept of capital T, or the cycle time. What we have is the bit duration. Okay, so the bit length here changes slightly to become the distance that the signal is allowed to occupy, okay, in a time equals to the bit duration. Okay, so it's the distance that the signal is allowed to occupy in a time equals to the bit duration. Okay, so in other words, if we have a transmission line that transfers a digital signal, okay, so we have, like, for example, 1 voltage level like this, and then it changes to another voltage level. So this is what we refer to as the bit duration. So what is this distance on the transmission medium? This distance again depends on the propagation speed. Okay, so again, the bit length, similar to the wavelength, equals to the propagation speed times the bit duration. The propagation speed times the bit duration, as opposed to the cycle duration, because for the case of digital signal, we do not have a cycle. Okay, so this example here talks about the scenario that we have 100 page, a document that contains 100 pages, okay, and we want to send that document using 100 pages per minute. 100 pages per minute. So what is the required bit rate of the channel? So if I were to transfer this document, it's a digital document, and I want to transfer it over a transmission medium. So what would be the bit rate required on the transmission medium in order to transfer these 100 pages in 1 minute? So if we assume that we have each page like this, okay, is on average containing 24 lines, okay, and each line contains 80 characters, okay, and then in order to convert each character to bits, we have to represent it using ASCII codes, okay, so each character is represented using 8 bits. Then the problem simply becomes multiplying 100 pages by 24 lines by 80 characters by 8 bits per character, right? And this will give us the bit rate in terms of A. In terms of A, shabab. Bits per minute, شفت? Yes, bits per minute. Yes, that's that guy's focus. So bits per minute, okay? So it's either here, it's bits per minute, or here we have to divide this by 60 if we want to get this rate by bits per second. Okay, so remember that. Okay, so if we want to get this rate using a unit bits per second, then we have to divide this by 60. So this is so pay attention to the units very carefully. Okay. So this is a sorry. Yes. So there is a slight typo. Yeah, there is a slight typo in the slide. So you have to divide by 60 if you want to get it using bits per second. Okay. All right. So this slide is extremely important, and it actually summarizes يعني 2 chapters in the course, or maybe 1/3 of the course. So this slide has to be really absorbed يعني really carefully. So for digital signal, to transfer digital signal over any kind of transmission medium, we have 2 methods or 2 broad categories of methods. Okay, we have what we call baseband transmission. Baseband transmission. Okay, by baseband transmission here, I mean that we take the digital signal and we transfer it as is. So that the digital signal will be transferred as is on the transmission medium. Okay. So what is the problem here? As I said before, in the past we never had to, in the very past, yani, you probably didn't live these days at all. In the very old past, we used to transfer analog signals over the transmission medium. So we never had to deal with digital signal. So what is the problem with digital signal? What is the problem with transferring digital signals over any transmission medium? We talked about that last time when we said that, remember, any digital signal that has abrupt change like this, okay, if we need to represent this in the frequency domain, what is this corresponds in the frequency domain, ya shabab? Infinite frequency, right? Because the frequency is what? Is the rate of change per unit time, right? So here we have a rate of change, so we have abrupt change in a 0 time. So what is the frequency that corresponds to this? Infinity, right? So in other words, this signal, if I were to convert this signal to the frequency domain, this signal will have infinite frequency components, right? So this is very challenging. Why? Because we never have in practice, we don't have a transmission medium that can support infinite frequency components. We don't have that, even fiber optics. Okay? We do not have any transmission medium on Earth that has infinite frequency support. So all types of transmission medium, they have low pass or band pass, okay, effect, band pass filter effect. In other words, whether it's low pass or band pass, all these frequency components are, removed. So if you transfer the digital signal over any type of transmission medium, the output here will not look exactly similar to the digital signal, because this transmission medium is going to cut off all the very high frequency components of the signal, whether you like it or not. ماشي? So this is one piece of bad news that we have if we want to use baseband transmission, which means that we send the digital signal on any transmission medium as is without any manipulation. Okay, so in that case, you will end up with infinite frequency components of the digital signal, and the transmission medium, whether you like it or not, is going to cut off all these high frequency components. ماشي كده؟ So this is bad news. So that's why digital communication came about in recent decades, maybe 4 or 5 decades back. Before that, people used to transfer analog signals over the transmission medium, okay? And they were able to deal with analog signals because analog signals, you never have these abrupt changes, okay? You never have these abrupt changes. So you have no infinite frequency components, in which case we were able to deal with that, to transfer it over transmission media, different types of transmission media. We used to deal with that very easily. However, as we said, the motivation behind digital signals now is that we need to represent zeros and ones in order to be able to process these zeros and ones efficiently in the digital domain, and we know how to do that very easily and very efficiently. However, if we start thinking about transmitting these digital signals over any transmission medium, this is what's going to happen. All right? So that's the bad news. Is there any good news? Well, the good news is, remember, what is our objective here? What is our objective at the receiver side? Our objective at the receiver side is to recover the ones and zeros, right? Okay, so if we assume that we remove all the very high frequency components from the signal will look like this. Okay, which means that all these abrupt changes will be eliminated, and the signal becomes, in a way, analog signal. Okay, type, can I still recover the ones and zeros from this type of signal? Probably yes, right? Probably still yes. So the fact that these high frequency components have been removed from the signal, okay, it's not extremely bad, because I still can recover the ones and zeros from the signal, even if the signal is approximated by transmitting this signal through a transmission medium. And we will explain this in a lot more details later on. Type, can I get around these infinite frequency components? قال لك yes, you can. You can use what we call بقى broadband transmission. By broadband transmission, we will not transfer the signal as is. We will not transfer the signal as is. What we will do is that first, we will convert this digital signal, okay, which has, as we said, abrupt change. We will convert it first to analog signal from the beginning at the transmitter side. Okay, so for example, we can convert this to a sine wave that looks like this. Okay, and then it has a certain big amplitude, and then the zero will represent it using a small sine wave with a lower amplitude. Okay, so this way, if we convert it to an analog signal like this, and we transfer it over the transmission medium, remember this analog signal now has a certain minimum frequency and maximum frequency. It does not have infinite frequency components anymore. معايا يا شباب؟ تمام؟ So if we convert the digital signal to analog signal like this, we don't have the problem of infinite frequency components. So if we transfer a signal like this over this transmission medium, maybe we will succeed. We will not have any issues. And on the other side, again, I know from the amplitude of the sine wave that this is 1, and I know the amplitude from this sine wave that this is a 0, so I will be able to recover the 1s and 0s at the receiver side easily, right? And I did not have the problem of the transmission medium cutting off all the infinite frequency components. طيب. أيوة ماجد, do you have a question? لا, هو بيحاول العكس من ديجيتال لانالوج. هو بيحاول من ديجيتال لانالوج. ايوه, بيحاول من ديجيتال يعني بمعنى ايه؟ ان هو بياخد الديجيتال سيجنال دي, تمام, وبيقوم محولها لانالوج سيجنال using a sine wave. Okay, by using a sine wave, the sine wave is an analog signal, and this is actually the simplest form of the analog signal. By doing this, خلاص, we don't have infinite frequency components anymore, right? لأن السيجنال دي it does not have any abrupt changes, صح؟ تمام? It does not have any abrupt changes. فبالتالي انت you don't have infinite frequency components like the case of the digital signal. We don't have that. صح؟ فبالتالي if we can transmit it over a transmission medium, and transmission medium يعني all the transmission media on earth, they have either low pass or band pass effect. بمعنى ان هم they either have maximum frequency they can provide, or they have maximum and minimum frequency they can support. Okay, you cannot have a transmission medium that has, you know, infinite frequency support. That does not exist. Okay? So whether you like it or not, the high frequency components are going to be cut off. But this type of signal is more transmission friendly. Let's put it this way. ماشي كده؟ يعني these analog signals in general are more transmission friendly. ماشي؟ Digital signals, okay, are not transmission friendly by nature. In other words, if you transfer the digital signal directly on the transmission medium, the infinite frequency components are going to be cut off, which will result in signal approximation. متابع يا مجد؟ تمام؟ تمام؟ that's the difference between baseband transmission and broadband transmission. Broadband transmission converts the digital signal to analog signal. Okay? Baseband transmission transfers the digital signal as is, which will result in signal approximation at the output of the transmission medium. So that's the difference. Type. What are some examples of baseband transmission? Well, all types of wired, almost all يعني, types of wired standards that we talked about, they use baseband transmission. ماشي؟ يعني all types of Ethernet, point to point, PPP, 802.3 الكلام ده, all of them they use baseband transmission. Okay? Which means that when we convert the data into ones and zeros, we transfer the digital signal. طبعا digital signal here could be non-return to zero, could be Manchester, could be anything, and we will learn that in the next chapter in details. Okay? Whatever line coding techniques, we will convert the ones and zeros into digital signal, and we will transfer the signal, the digital signal as is on the transmission medium. Okay? طيب. Baseband transmission needs a dedicated medium, okay, with one transmission only occupying the channel. Why? Because remember, we transfer the signal in the low frequency domain, right? هتقول لي طب ازاي ما احنا اتكلمنا عن we talked about multi-access techniques for wired for Ethernet. Yes, but remember we told you that if you have two nodes sending on the shared medium at the same time, what used to happen? Collision, exactly. So if you have two nodes sending on the transmission medium at the same time, collision will happen. In other words, only one node is allowed to occupy the transmission medium at any point of time. Why? Because we are talking about baseband transmission. All the digital signals are transferred in the low frequency domain. طيب, isn't that the case for the broadband? No. Why? طيب, if we have two nodes sending at the exact same time, can we have the two nodes send concurrently at the same time without having collision? That's بقى a tricky question. And how? اللي هجاوب بقى على السؤال ده بقى هو بقى اللي يستحق فعلا يعني بونص يعني. The question is, can I have two nodes transmit at the exact same time without having collision, and how? اتفضل يا احمد. different bands معناها different frequency يا احمد, صح؟ برافو عليك يا احمد, صحيح. So I can have two nodes transmit at the exact same time without having collision. How? If we convert two baseband, if two nodes, if we look at the frequency domain عشان نعرف يعني أهمية بقى frequency domain, the importance of representing the signals in the frequency domain. If I have two nodes transmitting in the baseband, okay, the first, both of them will be like this, okay, because both of them, they transfer in baseband. So if you have two signals overlapping in the frequency domain, you cannot have any kind of filter, or you cannot distinguish anyone from the other. So both of them will be noise to you, and you cannot really detect any signal from the other. However, if we use, so this is baseband, okay? If we use broadband transmission, what you could do is that you can use different carrier frequency. مش احنا قلنا ان the digital signal in broadband, it gets represented by using a sine wave. sine wave with different amplitude like this, right? So if you change the sine wave frequency for each of these two signals, right? One will have a sine wave of center frequency f1 and the other one is f2. You end up with two signals that look like this. The first one will look like this, and the second one will look like this. So this is signal 1 and this is signal 2. So these two signals are transmitting at the exact same time. However, one is using a sine wave with a center frequency f1, and the other is using a same sine wave with higher frequency, but it looks like something like this. Okay. So in that case, the two sine waves are sent at the exact same time. However, in the frequency domain, they look like this. Okay. And at the receiver side, I can easily use some filter here or here to isolate or to extract one signal from the other. ماشي يا شباب? Anyone not following this concept? Because this concept is extremely important. So based on this, broadband transmission, in fact, allows two or more actually nodes to send at the exact same time if we are careful enough to use different frequency for each of these signals. ماشي كده؟ So what is the example? احنا قلنا the example for baseband transmission is all kind of Ethernet or all kind of wired communication standards that we have talked about in network 1. So in that case, we told you that if two nodes send at the same time, collision will happen because of this. Okay. So what is an example of broadband transmission? Any standards, any technology, okay, communication technology that uses broadband transmission. حسين تفضل. Okay, what else? What else? Any type of wireless communication uses broadband transmission. Why? Why? Because remember, for wireless communications, okay, we have everybody is sharing one transmission medium. صح ولا لا? Which is the air. Okay? So all of us are sharing one transmission medium, which in that case, the air. So we all transfer the wireless signal through the air. Okay? So can we say that we have to use that we can use baseband? You cannot use baseband because you are sharing the transmission medium by default. Okay? And you cannot restrict all nodes in the same range to transmit like what we used to do for Ethernet. Because remember, even people who are using Wi-Fi, they share the same transmission medium like people who are using Bluetooth. They share the same medium like people who are using 3G, 4G, 5G, all of them. They use the exact same transmission medium. So theoretically speaking, if the Wi-Fi signal and the 4G signal, it's transmitted at the same time, at the same frequency, again, there is high level of interference. We call it interference, which is a type of collision. ماشي? However, the fact that we, as users, we enjoy, Bluetooth and Wi-Fi and 4G and 5G all at the same time is because of the fact that each of these services, it uses different frequency band. Different frequency band. Okay? So for example, Wi-Fi, it uses 2.4 gigahertz. 4G, it may actually use 800 megahertz, or it could use 1.2 gigahertz, and so on. ايوه يا ماجد، اتفضل اتفضل. Okay. Okay, so that's a good question. So if you have transmission medium like this, okay, and you have some transmission going on, and at the same time you have two users, okay, they are exchanging some wireless transmission, right? So is there any kind of interference or any kind of overlap between the two? The answer is no. No. Why? Because remember, this is guided transmission. This is guided transmission. You're not sharing the same transmission medium in that case. So this communication is happening on a totally separate transmission medium from this one. So in that case, you do not have any kind of collision or interference or crosstalk between the two. Why? Because we talked about the fact that UTP or STP, they have some isolation, and they have braided copper shield and so on. So to prevent all kind of external interference and crosstalk and all of this, right? We talked about this. So all types of guided media, okay, they do not have interference with other transmission media. The problem here becomes if you have two users, okay, here, and two users here, and these are exchanging two different wireless communications. These four users, they are using the same transmission medium in that case. Okay, so the only way you can have no interference between these two types of communication is ايه بقى يا ماجد؟ قول انت. Is if they use ايه بقى؟ ايوه، الله ينور عليك، بالظبط كده. They have to use different frequency, and that only happens for the case of a broadband. عامله زي الراديو بالظبط. الراديو all types of radio communication, they use broadband transmission, where different radio channels are transferred over different frequency bands. Okay, عندك مثلا FM. FM uses channels in the range of 108 megahertz. Okay, AM channels, they use frequency ranges in the kilohertz. So the channels for AM, okay, they never interfere with channels from FM. They never interfere with channels from Bluetooth. They never interfere with channels from Wi-Fi, although sometimes they do. And if they do, there will be some interference, and we'll have to deal with it. Wi-Fi uses a different frequency range from 4G, from 5G, and so on. So any types of concurrent communication over wireless has to happen through different frequency. Otherwise, we call that these two transmissions, they interfere with each other. Okay, so broadband transmission, okay, allows us to convert the digital signal to analog before we transmit, and that allows us to change the frequency, okay, of this channel in order to allow this channel to flow into the air easily without interfering with others. أيوة محمد، عندك سؤال؟ اتفضل. Frequency. Yes. Right. Yes. Exactly. That's exactly right. So that's why in Wi-Fi, it's in the range of 2.4 gigahertz. Okay. However, Wi-Fi internally divides the bandwidth into 11 and sometimes 64 different small channels. Okay. So one at 2.41 gigahertz, one at 2.42 gigahertz, one at 2.43, and so on, so that you can have multiple nodes communicating using Wi-Fi at the exact same time. Okay, so each standard defines a certain bandwidth, and inside that bandwidth, they subdivide it into smaller channels in order to have concurrent communication. All of this again uses the concept of broadband transmission. As long as we can convert the digital signal to analog signal before transmission, that allows us to change the frequency of these analog signals as we wish in order to facilitate concurrent communications between multiple nodes. That's not the case for baseband, because for baseband, we do not manipulate the signal. We transfer the digital signal as is, and that's the problem now, because that's why we told you that for Ethernet, if two nodes transfer the signal at the same time, collision will happen. You cannot have multiple nodes sending at the exact same time, because by default, baseband using the same frequency band, right? So that's why you are not allowed to transfer two signals at the exact same time. Type. The question is, again, it's a very tricky question. We said that broadband transmission is used for wireless and for radio, right? Is there any standard for wired communication that uses the concept of broadband transmission? So we said that for wired, we always use baseband, okay? And for wireless, we use broadband. Is there an exception for wired technology that uses the concept of broadband? Yes. I'm not expecting anyone to know. حد عارف? Yeah, go ahead, Daniel. Well, fiber optic is really complicated. It's not a representative example really. But there is a technology that's it was very common at certain point of time. I'm not sure if you've heard about it, which is called asymmetric digital subscriber line, or ADSL. ADSL existed before the fiber to home technology that we have to connect to the internet nowadays. So before that, we used to use a technology called ADSL. Okay, so the idea of ADSL is the fact that we have already a network that has been around for decades, which is the telephone network. Okay, we have a network called public switched telephone network, which is the network for landlines. Okay, of course, some of us do not actually have landlines at home now, but this actually existed a long time back. So landlines have been already deployed, and their infrastructure for landlines has been already there. So now we need to have access to the internet. So the first thing that they thought about is that why not to use the same telephone lines that we have at home to transfer or to download some data from the internet. Okay, so we connect to Ooredoo through the landlines. So we might as well use this landlines for communication over the internet. And the idea was the fact that, okay, so our voice itself has a bandwidth of 4 kilohertz. Okay, these telephone lines, however, they can support bandwidth or frequency higher than even 1 megahertz. Okay, so the idea is, can we use this remaining part, okay, to transfer some data over the internet, to download and upload data over the internet? So what they did is that they used what we call ADSL modems. Okay, so the exact purpose of these modems is to convert the digital signal of our data into analog signal in the remaining range above 4 kilohertz. واضح يا شباب؟ So in other words, we have our telephone lines. Our telephone lines, they connect to the service provider. Okay, so they said, okay, so let's have our own computers. We connect with a modem. Okay, and from this modem, we will use some kind of a splitter like this or mixer. Okay, that converts our data into a digital signal, and then the modem converts the digital signal to analog signal in this range above 4 kilohertz. And then we transfer this over the same telephone line. And this was a brilliant idea, by the way, and we used to use ADSL until very recently, until the fiber infrastructure has been built. So ADSL is another example of broadband transmission over wired network. Okay, so we kind of overlay our digital data over the same telephone line that's used to transfer voice signal. ماشي كده؟ So this is another example of broadband transmission for wired technology. See how much time we took for this slide, because it's extremely important. So again, to transfer digital data over transmission medium, we have two categories of methods. Baseband transmission is to transfer the digital signal as is, and in that case, we have the challenge of cutting the infinite frequency components, and this requires the fact that the transmission medium has to be dedicated for one single transmission at any point of time. For broadband transmission, we have to convert first the digital data to analog before transmission, okay? And that's, as we said here, the frequency components above F1 will have to be cut off for all types of radio communication. طيب, so any transmission medium, as I said before, it has either low pass filter effect or band pass filter effect. If it supports zero component, then it's low pass. The fact that this transmission medium has a frequency F1, or the maximum frequency, which is higher compared to the transmission medium at the bottom here, makes this transmission medium, okay, more capable of transferring the digital signal more accurately. Okay, because so the higher the maximum frequency supported by this transmission medium, the more accurate this transmission medium will be able to support the baseband transmission of the digital signals. So that's what we have. So any digital signal has infinite frequency components, right? And the challenge here is that any transmission medium has either low pass or band pass effect, which will make the signal look like this. So this signal, we call it approximation. Okay. So the signal, no matter what you do, the signal will have to be approximated. This is the bad news. The good news is this digital signal represents what? possibly, let's say this is a 1 and this is مثلا, let's say this is 0 0 0. Okay, so if we transfer the signal and the signal looks like this, can we still recover the ones and zeros? Yeah, most probably with good accuracy, we can say that this voltage is above 0, so we still can recognize that this is 1, and this is below 0, so this is 0 0 0, right? So even though the signal has been approximated, but we are still able to detect the ones and zeros from the signal. Okay, so just the fact that the signal has been approximated, it doesn't necessarily mean this is something bad and we cannot do this. We can still do this with some good signal estimators at the receiver side. We can still ones and zeros. So baseband transmission of a digital signal that preserves the shape of the digital signal is impossible. It's not possible unless we have infinite frequency support by the transmission medium. And that transmission medium does not exist in practice. It does not exist. Okay? So an example of a dedicated channel where the entire bandwidth is used at one point of time is all the LAN standards that we have studied in Network 1. All types of LAN standards. Okay? All types of Ethernet standards, point-to-point, all of these, they use baseband transmission. So you cannot share, okay, the line between two nodes that transfer the signal at the exact same time. You cannot do that because both of them, they transfer baseband and they will have collision in that case. Type. So the low pass. Yes, Daniel, do you have a question? Well, because of many reasons. Broadband is much more complicated because you have to have a transceiver that uses and supports multiple frequency bands at the same time. Whereas for baseband, you only need to deal with one frequency band only. So the transceiver itself, in terms of hardware design, will be much simpler, much simpler. Yes, it's a trade-off, of course. It's a trade-off. And for guided transmission, okay, you do not have that urgent need to have broadband because it's guided transmission anyway. So if you need to have two people communicating at the same time, use different wires, right? So you can have different wires. So any kind of communication happens between two entities on a guided medium, it will not interfere with other guided medium because it's guided medium. The problem always with wireless is the fact that we all share one transmission medium, and that's why we need some kind of broadband transmission. We have no way around it. We have no other solution. Okay. Type. So the low pass channel, whether we like it or not, are going to approximate the digital signal with an analog signal. Okay. So the approximation depends on the available bandwidth, the maximum frequency that this transmission medium supports, okay, dictates the level of approximation, okay, of that digital signal. Type. The question is, what is the roughest approximation of a digital signal? What is the roughest approximation of a digital signal? Well, the roughest approximation, if we can think about the extreme case, that we can represent the digital signal using the simplest form of an analog signal, which is shabab. What is that? What is the simplest form of an analog signal? Sine wave, right? So the question is, can we use sine wave to represent digital signal? Let's see. This example talks about يعني 3 different bits, okay, 3 different bits, and we want to have all the different combinations. Even if we increase it to 4, by the way, the example is still valid. So if you have 3 bits, okay, the different combinations that we have is either 000 or 001 and 010 and so on, right? So we have all the 8 different combinations, right? So my constraint now is that I need to use one single sine wave to represent these 3 bits. So I can use sine wave with different frequency, that's fine, but it's only one sine wave to represent these 3 bits. Can we do that? Yes. So I can use one sine wave with frequency 0, right, to represent 000. I can do that. If I have 001, I can use incomplete sine wave like this, okay? And even if I increase, if that's why I told you, even if it's 4 bits, okay, I can still do that. So this sine wave now, it's one single sine wave to represent the 3 zeros. هتقولي how come? Yes, we can still do that, because at the receiver side we can still say, oh, okay, so this part, if I know the bit duration, I can say in this part the amplitude of the sine wave is negative, so it is 0. And here the amplitude of the sine wave is still negative, so the bit is 0. And here the amplitude of the sine wave is positive, then the bit is 1. So from a single sine wave, I was able to represent 3 or even 4 bits. Okay, and this is the roughest approximation. So this case, by the way, is exactly like this case. Is exactly like this case. Is exactly like this case. That's if you have, so if you have one change of bits from the zeros to ones or from the ones to 0. In other words, I have 3 bits with only one change, one transition. Okay, it's either the 001 or 011 or 100 or 110. Okay, so all these 4 cases, okay, they represent similar case where I can use one single sine wave to represent 4 bits. So if I have n bits per second, okay, what is the frequency of the sine wave? It's n over 4, right? Which is this component here. So either I have a sine wave with frequency 0, which is this component, or I have a sine wave with frequency n over 4, because I can use one single cycle of a sine wave to represent 4 bits. ماشي? Or I have the worst case where I have two changes. If I have 2 changes like this within the 3 bits. So this case is similar to this case. Okay? So for these 2 cases now, I have two changes, 2 abrupt changes. Okay? So in that case, I can use one sine wave cycle. See here, one sine wave cycle to represent 2 bits only. So for 3 bits or 4 bits, I need 2 cycles of sine wave. واضح يا شباب? So in that particular case, the frequency is n over 2, which is this component. Okay? So using all these 3-bit combinations, I can represent them using one single sine wave with either 0 frequency, n over 4 frequency, or n over 2 frequency. So in that case, what is the bandwidth of this? What is the bandwidth of this signal, by the way? It is the maximum frequency minus the minimum frequency, so it's n over 2. Right? So I can use one single sine wave to represent all the 3, and actually I can use 4 bits hatta. Okay? So the bandwidth will be n over 2, and this is the roughest. This is the roughest approximation. Okay? So in other words, if you have a specific bandwidth, you can use a bit rate of double the bandwidth. Okay. Type. So approximation has a bandwidth of n over 2. So it's always a multiple of n over 2. Okay. Roughest approximation of any signal. Can we have a better approximation? Yes, you can. You can combine. مش احنا قلنا ان two sine waves they can combine to form what we call a composite signal. So this is a composite signal that's composed of two sine waves. And as you can see, compared to this one, this sine wave is better in representing the original signal more than one single sine wave, right? So the changes here are better than here. Okay, and this is for this we have three different sine waves, and here the change is even better. So I can use two sine waves or three sine waves to represent the digital signal. Okay, so in that case we call it two harmonics, the one and the third harmonic. So it's either n over 2 or 3n over 2. And here we have three different sine waves where we use the single harmonic or 3 or 5. So we have three different harmonics to represent that signal. And if we use three harmonics, the approximation will be more accurate. Okay, it's still an approximation, but it's more accurate. واضح كده يا شباب? So we can use either one single sine wave or two sine waves, which is the first harmonic and the third harmonic, or three sine waves, which is the 1, 3rd, and 5th harmonic. Here, I'm using two sine waves in a composite form. Here, I'm using two sine waves in a composite form. Okay, so one sine wave with a frequency n over 2 and one sine wave with a frequency 3n over 2. That's why we call it first and third harmonic. So it's always a multiple. It's always a multiple of n over 2, because we said here that the roughest. So in other words, if it's 1 and 3rd harmonic, it's either 0 here. It's either 0, 3n over 4, and 3n over 2, because 3n over 2 is the bandwidth. If it's 1, 3rd, and 5th, again it's 0, or 5n over 4, or 5n over 2. So again, the bandwidth is 5n over 2. So it's always multiple of n over 2. ماشي كده؟ ماشي؟ So in baseband transmission, the required bandwidth is proportional طبعا to the bit rate. Yes, Daniel. n over no. طيب. So in baseband transmission, the required bandwidth is proportional to the bit rate, and we know that. If we need to send bits faster, then we need more bandwidth. That's a fact. We cannot get out of this. So this table shows us that if we have n bits, we can have single harmonic to represent this, in which case it's the bandwidth is n over 2. Okay, so if you have 1 kilobits per second, the bandwidth is 5 hertz. Or if you have two harmonics, the 1 and a 3rd, then it's 3 times the bandwidth, so it's 1.5 kilohertz, or 5 times the bandwidth, which is 2.5 kilohertz. All right, so that's so from 1 harmonic to 2 harmonics to 3 harmonics, I'm going through more accurate representation of. All right. So this example shows the low pass channel if we need to send 1 megabits per second. So if we use one single harmonic, so the bandwidth is n over 2, which is 500 kilohertz, or 3 times or 5 times. So that's very easy. Example بقى now, it shows the reverse. If we have a low pass channel with bandwidth 100 kilohertz, okay, what is the maximum bit rate? The maximum bit rate. When do we have the maximum bit rate, ya shabab? when the approximation is ايه؟ يعني I use 1 harmonic ولا 2 harmonics ولا 3 harmonics؟ لا. The maximum is at 1 harmonic. Why? Because the bandwidth is ايه؟ The bandwidth is proportional to the bit rate, right? So it's either here we have, for one single harmonic, we have 1/2, or we have 3/2, or we have 5/2, which means that the if we get n, so n is the bandwidth multiplied by 2, or multiplied by 2/3, صح? Or multiplied by 2/5. So which one gives me the maximum? The 2. Which makes sense because this is the roughest approximation. So if I have a specific bandwidth and I want to fit or squeeze maximum bits in that bandwidth, then I use the roughest approximation. The roughest approximation will allow me to squeeze many bits in that same bandwidth, which in that case using one single harmonic. ماشي? So that's why it's a 2 kilobits per second. This is the maximum bandwidth. ماشي كده؟ ماشي? So that's what we talked about. So we'll stop here at the broadband transmission. So we'll stop at this point. I need to